Okay, so Sumesh is not here today, so I'm just substituting for him. So we're going to talk about. I kind of titled this, this particular lecture as something about different fluids, viscosity, and its measurement. A lot of contents that I've, kind of compiled from different sources. The references you can see there. Okay, if you want to know more about each of some of the things that are going to be discussed today, you would have to go to those sources and then read a little bit. Okay, we'll just begin by just defining what is viscosity. Okay, I think Sumesh did in the last class about viscosity of the gases, right? And talked about T power 1.5 relationship that you get for gases. In a layman's term, okay, you could just say that viscosity is you can think about it as resistance to flow, right? That's a laymannish definition of viscosity. And in SI units, what is the unit of viscosity? It's, what is that? It's Pascal second, right? It's Pascal second. And so you see a list here. Okay, basically there are different fluids, and the viscosity of each of these fluids are kind of listed there. Think about water has a viscosity of like 1×10⁻³ Pascal second. Okay, and so now there are two columns here, right? There's one is viscosity, the other one is density. If you take a closer look at these, the numbers for different fluids, it turns out that it is not necessary that something that is highly dense, okay, need not be more viscous, right? I hope all of you know this fact that, for example, if I take a look at, say, mercury, for example, density is really high, right? Because its viscosity, okay, is just about that of water, right? Whereas the density of water is about 1000, right? So therefore, your density and viscosity, they don't go, hand in hand. Okay, so it need not be that something that is more dense is more viscous. Okay, that's really not true. So if you want to tell somebody that when people say that viscosity is a kind of a quantitative measure of resistance, have you kind of experienced if you want to tell you in a practical way, how would you tell somebody what is viscosity? You could think of like say a simple case of running, right? If I take two cases, one is I'm running in water, other one is running in air, right? The fact that it's much more difficult for you to run in water, okay, you can think about this in terms of the viscosity, right? The resistance that the fluid offers. And actually that's kind of quite clear if you look at the viscosity values. If you take water, it's 1×10⁻³. If you take air, it's 1.8 10⁻⁵. Okay, the ratio of viscosity is about 50. Okay, the fact that the water is definitely 50 times more viscous than air basically gives you this additional resistance, which because of which you kind of run much slower, okay, in spite of putting the same effort, right? So that's you could think of arguments like that to really think about the resistance that that a fluid offers, right? Now there are different types of fluids. I'm sure all of you have kind of learned this at some point for sure. So there's actually a plot of your shear stress as a function of shear rate, and then there's another plot next to it which is your viscosity as a function of shear rate, right? Do you know what these do you know typical class of fluids that kind of obey such behavior? Your, what is that? Newtonian fluids, right? All of you have heard of Newtonian fluids, and your stress is proportional to shear rate, plus if you measure viscosity as a function of shear rate, it turns out that the viscosity should be a constant, right? So all of you know about this. Okay, if you're not familiar with the terms, you will see that a lot of people use your gamma dot that you see here, right? Gamma dot, you can call it as rate of shear rate strain, right? Sorry, you can call it as shear rate, or you can also call it as a shear strain rate. Okay, that kind of comes from the simple argument, right? If you have this dv by dy, which is the velocity gradient, okay, I can express this dv as dx by dt, right? Distance by time. Okay, the change in length by original length I can actually express in terms of strain. Okay, and that strain divided by time is going to give you the strain rate. Okay, so your gamma dot, people either call it as strain rate, or you can also call it as a shear strain rate as well. Okay, you will see that different books use different kind of terminology, and you would have to be a little bit aware of these terms. Okay, and as you know, this is a classic case of Newtonian fluids. Okay, and it turns out that a lot of things that we use, they are not Newtonian, right? There are different. So before you go to different kinds of fluids, I just want to make a point about something called as a shear rates that are typically kind of exist in different processes. Okay, so what you see is the first column, it lists processes. The second one is what is called as a typical range of shear rates, and the third one is application. Okay, so it turns out that depending upon the processing conditions, your shear rates are going to be very, very different. Okay, what I mean by that is, if you have, like, say, a cream that you're trying to apply to your your body, for example, okay, and when you put your cream onto your on the body, and then if you're trying to rub it, okay, the kind of shear rate the material feels is very, very different, okay, than maybe putting an oil onto your hair, for example. Okay, so therefore, for example, a typical there's a list called rubbing. The typical shear rates would be 10 power 4 to 10 power 5 second inverse. That's really fast. Okay, that's really doing a very fast shearing. Okay, and there are also applications. For example, if you look at sedimentation of fine powders, you have a column of liquid and the particles are settling. Okay, in such cases the shear rates are very, very low, 10 power minus 4 to 10 power minus 6. Okay, that's too low. So therefore, there's also need to look at different fluids and then have an idea as to how does the material respond to different shear rates. Okay, so and again, it depends on the kind of fluids that you're dealing with and stuff like that. Okay, now again, I'm sure all of you know this particular plot, that there are typical material flow behavior that fluids exhibit. Okay, the top two plots are basically plots of shear stress versus shear rate. Okay, both of them basically taken from different sources. Okay, and I'm sure all of you are familiar with these terms, right? Dilatant fluid, pseudoplastic, yield stress fluids and stuff like that. Okay, I hope all of you know these terms, right? No, don't know? Okay, these are fairly simple. Okay, so now let's think about toothpaste. Okay, every morning you just go and take your toothpaste, and if you open the lid and if you want it to fall by gravity, it's never going to fall, right? Of course, if you have if I take, like, say, again, there are different types of toothpaste, but typically most toothpaste, if you want it to come by itself, it won't, right? Under the action of gravity, it won't. So for that to come out, you would have to apply some kind of pressure, right? Okay, now such materials, what happens, they won't come out until you apply a particular force. Okay, or you can think about it in terms of until you apply a certain stress, they won't come out. Okay, so if you look at the class of fluids represented by these two fluids, okay, you clearly see that I would have to apply a non-zero stress for the material to start flowing. Okay, and such fluids, okay, are called as yield fluids. Okay, or it's also called as a pseudoplastic fluids and stuff like that. Okay, so therefore, if you want them to flow, you would have to apply some minimum stress for them to start flowing. Okay, those are some class of fluids. Of course, you have this the Newtonian fluid, right? Again, it's very similar to what we saw in the previous plot. Your stress versus shear rate is a linear variation. That's your Newtonian fluid, and you can think about whenever you have this stress versus shear rate plot, you can think about slope of these plots. Okay, at any instant of shear rate, you can think about it it as giving a resistance. Okay, and as I mentioned, okay, that resistance is you can think about that in terms of viscosity. Okay, therefore, if I take a Newtonian fluid like here, your slope is constant. Therefore, if I were to measure viscosity, okay, the viscosity of my fluid is going to be constant, right? Because my slope is constant. Okay, now if you take other type of fluids, your viscosity could be changing as a function of shear rate. Okay, for all non-Newtonian fluids, your viscosity is going to be a function of your shear rate. Okay, now depending upon whether the viscosity of the fluid is decreasing if you increase the shear rate. If that is the case, such fluids are what is called as shear thinning fluids. Okay? These are the fluids where if you take these fluids and if you start shearing them, the viscosity goes down with shear rate. Okay? Such fluids are what are called as shear thinning fluid. On the contrary, there are fluids where the viscosity could increase as a function of shear rate. Such fluids are what are called as a shear thickening fluids. Okay? That is so basically your dilatant is also same as shear thinning, okay, and pseudoplastic is also same as shear thickening. I think it's the reverse. Okay, I think it's the reverse. So I'm sorry about that. It's the reverse, right? Because if I take a slope of these plots, now if I take say pseudoplastic for example, right, slope is initially constant. Now if I increase the shear rate strain, my slope is going to decrease, right? Okay, that is, it's a shear thinning fluid. Sorry about that. Oops. Okay, that's your shear thinning. Okay, and if I take a dilatant fluid, if I take slope at different points, okay, with shear rate, my slope is increasing. Therefore, my viscosity is going to be increasing if I increase the shear rate. They are what is called a shear thickening. Okay, yeah. So just to, I just want to make a point that there are different class of fluids, okay, and their viscosity need not be constant. It could be varying as a function of shear rate, and depending upon whether it increases, decreases, or remains constant, you can basically think about fluids in different, and the most of the fluids that you come across in daily life or or in industrial processes, they kind of fall into some of these categories. Okay. Okay. So now, okay. So the question would be, can you think of a fluid that could exhibit all different behavior? One fluid which can be both shear thinning, shear thickening, and Newtonian. So can you name some example of Newtonian fluids? What's that? A lot of fluid that you use, right? Water, honey, for example, all of that, right? So for them, if you measure viscosity as a function of shear rate, it's going to be a constant value. They're all Newtonian fluids. Any example of some fluid where the viscosity need not be constant? Have you thought of some example? You should go back and take a look at some nice videos on YouTube. Okay, there's a nice video of you take water, okay, then you mix what is called as a cornstarch. Okay, if you go on adding some cornstarch, at some point, okay, it starts behaving very some funny way. Okay, so there are nice videos where people have made like say a bathtub made of this fluid, and you can actually walk through the fluid. Okay, that's because at the instant of, if you're running through this fluid, at the instant of contact between your foot and the bathtub, the viscosity goes up very high. Okay, and that can actually support the whole weight of the person who's running on the bath. Okay, so a classic case of fluids, okay, which exhibit all these properties in one in the same fluid is an example of something called as a colloidal dispersions or nanoparticle dispersions. Okay, simple way to think about this would be these are slurries. Okay, it's a liquid with some particles. Okay, the particles could be very small in size, nanoparticles. It could be micron in size, or it could be even larger macroscopic particles. Okay, so what you're seeing in this plot is actually it's a plot of viscosity as a function of shear stress. You could also have instead of shear stress, I could have also plotted a shear rate as well. Okay, what you should note is that for each plot that you have, there's a parameter that is defined. Okay, that's called phi. Okay, and that phi is what is called as a volume fraction of particles in the fluid. Okay, phi is equal to 0 corresponds to a pure fluid without any particles. Okay, if I say like say phi is equal to 0.09, okay, that basically corresponds to a case where I have 9% of particles in the fluid. Similarly, if I say phi is equal to 50.50, you have 50% fluid and 50% particles, right. So, all that has been done here is they have subjected this fluid to a similar test of basically measuring viscosity as a function of your shear stress, okay, and as a function of different concentration is the result, right. And if you look at the low concentration data, okay, that is from about 0 to 0.18, you can see that the viscosity versus your shear rate is a flat line, okay. So, basically that is your Newtonian behavior, right. Right, that is your Newtonian behavior. Now, if you go a little bit higher in concentration, 0.34 and 0.28, okay, what you see is initially your viscosity is constant, and that is basically followed by a very small decrease, okay, and that small decrease, okay, is an example of a case where there is a shear thinning behavior, right. Now, if I go a little bit higher up in the concentration, it turns out that there is of course a decrease followed by an increase at a higher shear stress, okay. That is an example of a case where you have both shear thinning in this region and a shear thickening in this region, okay. So, and this phenomena of shear thickening actually has been exploited in a lot of applications. So, I have kind of given you some applications that one common example is a body armor, okay. So, whenever people have this bulletproof jackets, okay, what is there are recent developments where in between different layers of cloth, okay, what they put is these fluids, okay, which when a bullet penetrates at a very high force, it basically locally solidifies the material, okay, and thereby stopping the bullet from penetrating into the vest, okay. So there are applications of such material. So I just wanted to give you a little, okay. So now there's an understanding as to why this happens, okay. Okay, so the common the picture that people kind of think about is that the case where you have your shear your Newtonian behavior is a case where you have kind of a randomly distributed particles in your fluid, okay, and you are subjecting them to your shear flow, okay, right. And then if you go for a higher shear rate or shear stress, it turns out that there is some kind of a ordering, okay, and kind of particle form these lanes, okay, lines of particles, and these lines of particles essentially you can think about them as offering less resistance for the flow, okay. One way to think about this would be a randomly moving traffic versus traffic in a lane, okay. So now if you go higher up in the shear rate or shear stress, what happens is you are basically forming what are called as particulate clusters, okay. When you are trying to kind of shear them at a very high shear rate, all the particles are kind of brought together and you kind of form locally these clusters, okay, and these clusters kind of interlock, okay, and this interlocking of these clusters in a way leads to enhanced resistance, okay, thereby the viscosity goes up, okay. So this is a kind of understanding that people have about such fluids, okay. Okay, so that's about different types of fluids, just to give you a picture of different class of fluids, okay. So all that we have done so far is we have just said something about what is viscosity, and then we have kind of discussed different class of fluids, and I just took one example of a particular class of fluid where you see the Newtonian, non-Newtonian behavior in the same fluid, right. That's what we have done.